Welcome to my second tutorial on understanding constitutive models with incremental driver by testing them in representative elementary volume. Today we will follow with constitutive model that introduces a state variable, which is the void ratio, which we will introduce in initial conditions here as a new state variable with number of stateFs as 1, and then after the number of stateFs we have to introduce and to assign an initial value for the state variable, for example here void ratio as 0.9, and the model that we will implement is hypo-elastic. Once we will implement for sand, and I will give you in my GitHub account under session 2 you will have both a hypo-elastic material for sand with S and for clay with C. Also here you will see initial conditions for clay and for sand, and also the material parameters for sand and for clay. Nevertheless, in this tutorial we will go through the implementation for sand, but just for completeness you have it also for clay here and can test it. Let us now continue with the coding. So today the main highlight is not only the new state variable, but it is also a very powerful tool which is called tensor tools in Fortran. It is written, as said, in Fortran, and mainly it was written by Andrei Nemunis, who was also the developer of incremental driver. Nevertheless, throughout the years, in the Institute of Soil Mechanics and Rock Mechanics in Karlsruhe, as well as at the Ruhr University Bochum, we extended it to obtain also some more tensorial operations, and that's why it's now called tensor tools. These tensorial operations are, for example, it contains the tensor delta, so Kronecker delta. It contains different other tensors which are of more importance maybe sometimes. Then it contains the norm, which is the double contraction, and it uses and calculates the norm of a tensorial quantity. Then it contains, for example, the deviator. It contains the unit. But what is more important are these operations, as for example the double contraction, which now doesn't have to be coded for each double contraction in the umat, but can just be used by .xx if one wants to double contract two tensors, or the dyadic product without. One can use inverse to calculate the inverse of a fourth order tensor or of a second order tensor. And these t-pose to 3 and t-pose to 4 were added by me for uses of an isotropic clays. We will go through it in future tutorials. And what is also important are these map to strand, map to D, to stress, to T, to DDS, DDE, which are used to calculate between void notation and tensor notation. For example, map to strand calculates from a strain tensor to a strain vector. So to strand is always a vector, so in dyadic notation. And map to D would be the calculation from strand, so from the void notation of the strain to the tensorial notation. Map to stress is from tensorial stress to void stress, and map to T from void stress to a tensorial stress. Map to DDS, DDE is also mapped from Jacobian, which is a fourth order matrix, to a second order matrix, which is required by Abacus. That means you can simply code in tensorial format, and then just by using these operations you can again calculate everything in void notation and give that to Abacus, for example, or to incremental driver. Now, for example, it exists also the MB, which is very known. So the Mockley brackets, they are also coded here. And yeah, now let us continue with our hypo-elastic material for sand. First of all, in material models, we wanted to add a library with the different material models. That means here I have to write now hypo-elasticity for sand. So this was linear elasticity. The hypo-elasticity for sand, we will name it like this. And we will have also the hypo-elasticity for clay. As I said, not coded today, but we will code it. I will provide it for you in GitHub, and you can go through it. So C means clay and S means sand. And the hypoelastic model for sand has 3 material parameters, and it's defined here. Now we can code it in our subroutine, so hypoelasticity for sand. And the name that we defined here for this model has to be written at the beginning of parameters such that we can, that incremental driver can understand which model we want to use. So I prepared pretty much the whole umat except of 2 places. Let's go through it. So we have hypoplasticity for sand, and this is the interface which is not changed. Then what we have new is TB. So we have the stress named as TB, and it is a second order tensor. We have EPOR is the void ratio. We have EPSP is the strain in tensorial notation. So the increment of strain, but in tensorial notation. Then we have P as the mean effective pressure. We have nu as a parameter, which is called here, props 3. And we have K and G, the bulk and the shear modulus. We have P atmospheric. We have G0 as a material parameter, which is called here. And P atmospheric as well is called here, even though this is not in the real sense a material parameter, because it won't change from simulation to simulation. So here we see the parameters. We have hypoplasticity for sand, 3 parameters. G0, I took it from a SANISAN publication, P atmospheric as well, and nu is 0.3 assumed here. Then the other thing we have is TB. So I said TB is the stress in tensorial notation. And to initialize it, we have to use the stress, so in void notation, and to map it to T, to the stress in tensorial notation. The same happens for EPSP. So we map from strain in void notation to strain in tensorial notation. Then what we have here to initialize is also our other new state variable, which was the void ratio. So we can write then here, EPOR is equal to stative 1. Just very simple. Then P, so our mean effective pressure, is minus trace. Trace is also defined in tensor tools. So we have to use here tensor tools in order to use these operations. And then we can use trace, for example, for TB to build the summation of the diagonal terms of TB, of the stress tensor, and that is divided by 3. And we have the G, which is after, for example, the hypoplasticity that is used in SANISAN. It follows this formulation, G0 multiplied by P atmospheric multiplied by these other things, where EPOR is the void ratio, P is the mean effective pressure, and P atmospheric is the material parameter. Then we have the bulk modulus, which is in dependency of G and nu. We have a tensorial variable, which is used to calculate the stiffness tensor, where we have 3 multiplied by bulk modulus multiplied by this tensor, where again we use this out, which is the dyadic product, and we use unit to calculate the unit tensor of the Kronecker delta. So we are using here again tensor tools, which are really very, very important. Then we calculate here plus 2 multiplied by G multiplied by deviatoric part of the unit tensor. Then the next stress will be calculated as TB plus the stiffness tensor multiplied, so double contraction, with the strain increment tensor. The Jacobian is, of course, the stiffness tensor. And what we also have to update is our void ratio, which is the next state variable. So each state variable has to be updated. and it is plus 1.0 plus a torque multiplied by trace epsilon b. Then we have to export the state variables, but the abacus and also incremental driver needs stress and needs DDS DDE instead of TB and Jacobian. Therefore, we will map the TB, so the tensor, stress tensor, to Voigt notation of stress, and the Jacobian also to Voigt notation of the DDS DDE. We also defined here the Jacobian. And we have also to update the first state variable, which is the Voigt ratio. So this would be it with the coding of a hypo-elastic stiffness for sand, hypo-elastic umat for sand with a new state variable and in tensorial notation. So we just coded a completely tensorial form of a umat for the elastic part of sand. Now let us perform some tests, which we today won't be restricted only to undrained and to drained triaxial tests, but we will also continue with oedometric tests. For example, let us perform the oedometric test with Cartesian. So with Cartesian control would be that we restrict each component in Cartesian coordinate system. That means this is the first, the second, the third, and so on components. Here we are controlling the strain in vertical direction with negative sign. Then we are compressing the sample. And of course, in an oedometric test, the horizontal directions of the strains remain unchanged. And then we can just click on Start. Let us just do a debug, just to show you how you can debug the code. There you can put here a breakpoint. By double-click the breakpoint, it will disappear, then you won't debug anything. But if you click there, then you will have a breakpoint. And if you click on Start, then it will stop here. So it will make a pause there. Yeah. And here then you can read the things. For example, props. You see, okay, props are read, okay, it's 125, 100, and 0.3. This is what we prescribed here in parameters. And you can add another breakpoint and click on following. Then you will see, okay, G0 is good. P atmosphere is also prescribed well, and so on. We can now go farther and, for example, see how stress is being written in 6 components in vector notation, and TB is being written in 9 components and in tensorial notation, as we see it here. And it has been prescribed well. So well done, Tensor Tools. You have mapped really well from stress to tensor stress. Then we can see if trace TB is calculated well. So P should be 200 because we have prescribed for the initial condition 200 in the 3 directions. And we see here, okay, P is 200 and it's positive. Well, then G is calculated here, K here. You could even calculate it by hand and check if he calculated well, or like that you can find mistakes in future. Then here is the stiffness tensor, 4th order tensor, which we see here. So this debugging might be useful to check if one has errors or why something is not well reproducible. Now I will close the debug files and I will continue to run the simulation. So this simulation is run. And another possibility to run an oedometric test, it is an incremental driver prescribed as oedometric S1, where we control the stress in vertical direction, and oedometric E1 would be to control the strain in vertical direction. Of course, all of these tests have to render the same result. Let us conduct the same tests. So once with Cartesian, with minus 0.15 in vertical direction. Now with oedometric E1, so again, 0.15 in vertical direction. And we will change the output name, so at E1. Here it was just 1. And then also S1, so with stress control. Now let us plot them. So here I controlled the stress. I knew how much I have to get this strain. Therefore, I brought up this stress, but of course another stress could also be applied and we should have the same results, but not then with the same strain. So let us plot it now. I prepared the file to plot it. So we have here file 1 would be with linear elastic. It is not added here. You could do it as homework. File 2 would be with hypo-elasticity for clay, which I also didn't do and could be done as homework. And then file 3, 4, and 5 are the oedometric tests that we just performed with hypo-elasticity for sand. Let us look how it looks like. Yes, here in epsilon 1 versus sigma 1 space, and here in void ratio versus logarithm sigma 1 space. Of course, all curves lie at the same position and overlap each other because we just performed the same test with different controls. Let us now continue with an isotropic compression test. So an isotropic compression test can also be done with controls of Cartesian. Let me find it. Yeah, it's here. This is for clay. Nevertheless, we need it for sand, but I will just copy it and put there S. So I am prescribing here in vertical, horizontal, and 2 horizontal directions, minus 0.15. So compressing the sample with 15% strain. This is one possibility for running it. The other possibility would be to control roscoe variables. What are roscoe variables? In the incremental driver manual, it is, if you go inside it, you could search for roscoe. I cannot search it here because I have to load more pages, but they are defined here using roscoe's invariants. There you can either control delta P, delta Q, delta Z, delta T 1, 2, 1, 3, and 2, 3, or you can or you can prescribe epsilon volumetric, Q, Z, and so on. So I will here now prescribe delta epsilon volumetric. And that delta epsilon Q should be 0, of course. And to prescribe that, let us use these commandos. So we have here R for roscoe in the output. And then I will prescribe here delta epsilon volumetric of 0.45 because it was in all 3 directions 0.15. So 3 multiplied by 0.15 will be a volumetric strain of 0.45. And the other directions are 0. Let us run the test and then plot it. Plot both of them. So we have performed an isotropic test. Here I have also the isotropic of linear elastic, which you can also perform as homework. I have it for hypo-elastic clay and of course hypo-elastic sand with roscoe and with Cartesian coordinates. Let us plot them. Yeah, so here I am plotting all of them. You can, of course, erase some of them just to see the one for sand. And what I'm missing here is this one with Cartesian coordinates, and they will overlap each other. So the gray and the green one will just lie above each other as we see it here, the gray, and when the green one comes, it's overlapping. So here you could explore a little bit more with the hypo-elastic model for clay, where you have kappa, and the line with E0 minus kappa multiplied by logarithmus P should lie over the simulation of hypo-elastic for clay. That is just an information which we'll maybe go through when we introduce models for clay, and I know that there is much interest in models for clay. Therefore, I will look to continue in the next tutorial with modified ComClay. So now we performed isotropic and oedometric tests. Let us just conduct a triaxial CD test, and so with hypo-elasticity for sand, and triaxial CU test with hypo-elasticity for sand. I have prepared them here So CD would be here. And it's running. So the CD test is done. And let us plot them together with the linear elastic. So linear elastic 1 and 2, it was with different controls. And hypo-elastic for sand, we see it here and here. And the triaxial CU test would be hypo-elastic for sand, it's here. So we just form it and then we can plot them here. CU, yeah, would be here. So we don't see here the linear elastic simulations because they are just behind the hypoelastic one, because here they look all the same because it's elastic, but in Q epsilon 1 space not. We could even, so I also performed the ones with clay, with hypoelasticity for clay, and could plot them also here. You have just to uncomment these lines and then you will also see them here, the green line. And also in the drain test, you have just to uncomment the line 65 and underneath it was uncommented. Then you will see it here. Yeah. So that would be it for the hypoelastic model for sand. Let us just go quickly through the hypoelastic model for clay, where we have kappa. So the slope of the compression line during reloading or unloading, so the elastic one. Nu, the Poisson ratio. Then we have again the void ratio as a state variable, and the other state variables as we know. We have K, which is in a dependency of P and void ratio, so we don't need P atmospheric for the normalization. We have G that is in dependency of K and nu. Now we calculate the other tensors that we need, and of course the other things are the same. So the main changes between this umat and this umat are here in material parameters and in the calculation of K and G. Everything else must be the same. Everything I told you today can be found in my GitHub account in session 2. You can just download it and then open REV-Tafili tutorial.vf project and just run it. So it runs out from a box and you don't have to do anything. Also, the umats are all coded. So the state that is online is this state with these changes that we applied in this tutorial. Nevertheless, for your understanding or to exercise, you could do the change on your own. My main issue and my main purpose for these tutorials is to get you used how to use the incremental driver, how to use the test file, which tests can be performed and are described, such that you don't have to perform a Cartesian control for oedometric test, but can just do it by oedometric E1 or S1, which is much more simple, or the controls with roscoe invariants in order to perform an isotropic test or a non-drain triaxial test with UEQ, etc. And also how to add some new state variables in initial conditions and what is the main purpose of these tensor tools, which is really helpful when one wants to code material models in incremental driver or also in Fortran. So let us keep in touch and please provide me with feedback on which models you would like to see in these tutorials. I have in my schedule for the next times models on clay. The main interest lies on models with time dependency. Nevertheless, we cannot go to time dependency without introducing, for example, at least modified CAM clay to show the main purposes of models for clay. And afterwards, after modified CAM clay, I will go to time-dependent models for clays, maybe also introducing hypoplasticity and also my model AFISA. So I'm looking forward to your feedback and thank you for your attention. Bye.